everyone, and welcome to this very last video of our course on differential equations 1. In this last part of the course, we want to discuss maximum principles, which are some of the most useful tools you have if you want to study elliptic equations or parabolic equations, no matter whether they're linear or non-linear. So we've already seen in the last video a particular example of a maximum principle, and that was in the elliptic case, where we consider the function that depends only on a variable in space. So we consider the function w in the specific situation of a bounded domain of R2. So we have a function w of x and y, and we asked that the Laplacian of this function w is greater or equal to 0. Then we've seen that this simple condition of just the Laplacian having a sign guarantees that the maximum of our function w over the whole domain omega together with a boundary is always the same as the maximum of w just taken over the boundary of the domain. We've said in particular that this is very useful if you want to study elliptic equations, because in general you don't consider just a PDE on its own, but you consider a PDE together with some data. And the right type of thing to consider when you have an elliptic problem, which we've seen in the normal form involves the Laplacian, is actually boundary value problems. So you would consider such an elliptic PDE together with the condition that w prescribed on the boundary is some given function g, and then the maximum principle allows you to control the maximum over the whole domain in terms of just the maximum value of your data. And today we're going to see that the sort of analog statement also holds true for evolution equations that involve the heat operator. So we've seen two different types of evolution equations which describe the behavior of functions that don't just depend on a spatial variable x, but also on a time variable t. On the one hand, we had parabolic equations, for example, things involving the heat operator, and on the other hand, we had hyperbolic equations, things like the wave equation. And now you can never expect to get a maximum principle for the wave equation. That really just doesn't work. But for situations that involve the heat operator, everything works out, and we're again going to see that just the condition on the sign of the heat operator, here we're going to ask for wt minus Laplacian w is less than or equal to 0. Respectively, if you just have one spatial dimension, that just reads as wt minus wxx less than or equal to 0. Then you're guaranteed that the maximum of your function is controlled in terms of the maximum value of your data. Now, before we formulate a result, we have to talk a little bit more about what kind of domains we want to consider. And in particular, we want to talk about on what part of the domain I want to impose data, and on what part of the domain I want to consider the PDE, respectively on what part of the domain I want to impose this condition that the heat operator has a sign. So a typical situation that you might consider is you have some domain in space that can be in 2 dimensions or in 3 dimensions, for example, just the room that you sit in at the moment, and then you consider the behavior of a function defined on this space and defined on a time interval. Now I can't really draw 4-dimensional pictures, so let me draw the situation where my spatial domain is 2-dimensional, and then I'm going forward in time. So in this situation, you might have some domain, say omega like this down here. So that's your spatial domain in R2. And that you're going to impose at time t equals 0. I'm going to consider this here. Here I'm going to impose so-called initial values by prescribing w of x at time t equals 0 to be some function w0 of x. And you're going to prescribe this for all points in your domain, in your spatial domain omega. So in terms of you sitting in a room and considering the change of temperature, what you would prescribe is that you're given the initial temperature in every single point in your room. And then what you do is you consider a parabolic equation like this, so you can solve forward in time, but you can't solve backward in time. So my domain on which I consider everything is going to be some kind of cylinder type thing in space-time, so time goes in this direction. And I might consider this up to a certain sort of final time, t equals capital T up here. So then, in addition to my initial values, I also want to impose the behavior of the function on the boundary. So again, in the analogy of you sitting in a room and considering the temperature distribution, you want to know how warm your walls are going to be. So in addition to initial values, I'm going to impose boundary values. And that means at every single point on the boundary, I'm going to consider this point and the corresponding value for all times going forward. So I'm basically going to impose things on what you can think of as basically the walls of this glass. So I'm asking that W of now x and t is given by some function g of x and t, where my x is now constrained to be in the boundary of your spatial domain, but my time t is in the whole time interval, 0 up to t. So your space-time domain, this is going to be some kind of cylinder in R3. This would have another, in some sense, boundary just as a set, and that would be this sort of top part here, where you're considering t is equal capital T. But this part, sort of the set theoretical boundary, is very different from the other parts, from this initial part and the spatial boundary, because up here you're actually going to be able to determine the function W, for example, if you evolve by heat equation, just based on the initial and the boundary value. So this part up here should really be considered together with the rest of what you can think of sort of the interior of this domain, the interior of this glass. And we're going to consider the PDE, respectively the condition here Wt minus Laplacian of W less than or equal to 0 on the rest of the domain, and I call this omega capital T. So here this is omega, the interior of my spatial domain, cross the time interval that doesn't involve 0, but that involves the final time. And what we want to see is that if we are in a situation like that, then I can get information of W on this domain here based on just information on W on these 2 bits of the boundary. And together we're going to call this the so-called parabolic boundary. That's the part of the boundary where for a parabolic problem you're going to impose the data, so the initial values and the boundary values. Now you can formulate this for a 2-dimensional domain and then cross time, so a 3-dimensional domain in space-time. You could formulate it in n+1 dimensions, and everything really is exactly the same. For simplicity, we're just going to state the corresponding result for 2 dimensions, so 1 spatial dimension, 1 time dimension. What we, however, want to observe is that to state this result, it really doesn't matter that you're always having the same spatial domain. So I can just as well draw this picture and sort of have some walls which are a little bit curved, and everything is still going to work out as long as these sort of boundary curves, or here this boundary surface, still describes what corresponds to the behavior of the boundary going forward in time. Let me now make this precise in the 2-dimensional situation, and let me finally state what's the last theorem of our course. So let me state this result, and this result is theorem 4.3, which is the version of the maximum principle in the parabolic situation. As already mentioned, in the situation of the elliptic maximum principle, there's quite a lot of different versions of the maximum principle, and here we're just going to go for the simplest version because that will make our life easier for the proof, but it already gives you some insight of what a maximum principle can do and also a little bit of what it can't do. So how do we want to formulate this theorem? So let's first talk a little bit more about the domain. So we're asking here that we're in 1+1 dimension, so 1 spatial dimension, 1 time dimension, and we're considering a domain omega t, which is bounded by sort of different types of curves. So first of all, I want it to be bounded by the curve t equals 0, then by a curve t is capital T, which is sort of the final time that I consider. And then I want it to be bounded by some further curves. So now I can either consider a fixed interval here, say AB, and then just ask that this is always the interval that I consider going forward in time. Then I get some straight curves here. But more generally, I can change this domain and ask that going forward, I'm just going to always have some kind of interval here, and I'm going to describe the boundaries, the spatial boundaries, by some kind of curves, which what they shouldn't do is they shouldn't intersect, because then my whole domain collapses down to a point that makes no sense. And also, these curves shouldn't do something like going forward, going towards the future, and then deciding, no, thank you very much, I go and turn around and go back to the past somehow. That doesn't make sense to define the sort of behavior of an endpoint of an interval going forward in time. So the two conditions I ask of these curves that are called C1 and C2 is that C1 and C2 are curves, they should be smooth, so that they don't intersect. And they are never parallel to the x-axis. Because of course, if I had a curve that did something silly like going to the future, turning around, going back to the past, I need to have at least one point where this curve becomes horizontal, and hence I would violate this constraint. So if that's what I have, then let me assume that I have a function w that's defined on this whole thing, including the boundary, so from omega t into the reals, and this should please be continuous. And it should satisfy this main condition that my heat operator has a sign. So I ask that Wt minus Wxx is less than or equal to 0 in omega t. So that's everything except these three boundary curves. And if I know this, then I can conclude that my maximum over the whole domain, omega t of W, is the same as the maximum of W taken over the set where I impose data, and that's what we call the so-called parabolic boundary. So the part of the boundary where for a parabolic problem it's the right thing to impose data. So I'm writing this as boundary P of omega t, where in this situation the parabolic boundary of the domain is given by the initial interval, so AB cross 0, and then it's given by these boundary curves C1 and C2. So in the situation that we had before, so over here with this cylinder, where we had this omega t being a cylinder in space-time, the right thing to consider as parabolic boundary here would be the domain omega cross the time t equals 0, together with the boundary of omega cross the whole time interval 0t. So exactly the bits that I drew here in black, where I have initial values, respectively boundary values. So this is our last theorem. Of course, we'll celebrate the theorem with a little corollary afterwards so that the theorem doesn't get lonely. But before we can do this, we have to prove it. So how do we want to prove this? Well, in a first step, we want to actually ask for more than what we assume in the theorem. And what we want to ask is that we have a strict inequality. So step 1 is to assume that my function w satisfies the same conditions as before. In particular, it's continuous on the whole domain. It's differentiable enough, so twice in space, once in time, that we can make sense of the heat operator. And I ask that Wt minus Wxx is actually strictly less than 0 in my whole omega t. And what I do in this situation is that I claim that the only point where I can achieve a maximum is on the parabolic boundary. So I claim that the maximum of W is only achieved on the parabolic boundary of omega t. So in order to prove this, well, let's first make sure we actually have a maximum. So let me note that as Wt, the closure, is bounded. So in all of this, I've said omega is always a bounded domain, hence omega across a bounded time interval is also bounded in my space-time. I have the closure, so this is bounded and closed. So it's compact. And as my function w is continuous, I know that the function w actually achieves its maximum So what I conclude is that there exists a point that I call P star, so that's X star T star, in my domain omega t closure, so that W at this point P star is the maximum of W over the whole omega t bar. Now, what do I need to do in order to conclude that this point is on the parabolic boundary? So my parabolic boundary, remember, is something like this. So I'm having this sort of domain like this. Here's my initial curve. Here's my t is equal to 0. Sorry, my t is equal capital T. Here's t equals 0. So in order to conclude that the maximum is achieved on one of these three curves, I have to exclude the possibility that the maximum is achieved in the interior here somewhere, or that the maximum is achieved on this top line, where the important thing is we include the endpoints of these boundary curves here in the parabolic boundary. So I have to exclude that I can achieve a maximum in a point in this interval somewhere in the interior. So we argue by contradiction, and let me suppose that P star is not in the parabolic boundary. Then either I know that P star is given by some X star T star in my domain omega t, where T star is less than capital T, or I have the same thing, but T star is equal capital T. Now, in both situations, there's one thing which is the same, and that's I can move towards both the left and the right in X direction. So because I'm in the interior here, I can of course move both in X direction and T direction, at least for a little bit. But up here, I can only move freely in X direction, and I have to be more careful in what direction I can move with respect to time. But in both situations, what I can do is I have that the map that takes X maps to W of T star X achieves an interior maximum at X is equal X star. And we know already from A levels, if you have an interior maximum of a function in one variable, so I conclude that Wx of P star is equal to 0, and Wxx of P star, I have a max, so this is less than or equal to 0. On the other hand, in the first case, I can also move freely both forward in time and backward in time, and I still have a maximum. So by the same argument, in the first case, the derivative with respect to the time also needs to vanish, so I get Wt of P star is equal to 0. I really shouldn't talk about second derivatives in time because they might not even exist. I'm not asking for that because all I'm asking is that it's differentiable once in time, twice in space. So in the first case, we have this, while in the second case, we can't say that Wt needs to vanish because I can only move backwards in time. However, I know that if I move backwards in time, then I just decrease my W, I cannot increase it. And therefore, what I get is that my time derivative of P star, so this might not be equal to 0, but actually what it needs to be is greater or equal to 0, because if it was strictly less than 0, then I would arrive at this point with a negative slope, so it can't be that I've had a maximum. And that's good enough in both situations, so I conclude in both situations that Wt minus Wxx at this one particular point P star, so the first bit is greater or equal to 0, the second bit is less than or equal to 0, comes with a minus sign, this is greater or equal to 0, and that's a contradiction to our assumption that my function satisfies the stricter condition that Wt minus Wxx is strictly negative in omega t. So that proves the claim in this first step where we have a stronger assumption. And now the second step is to just say if I don't have a strict inequality but a weak inequality, then I want to modify my function W in order to be able to use an auxiliary function and to still be able to apply the first step and to conclude that the maximum over the whole domain is the same as the maximum over the parabolic boundary. Now there's an important difference in that proof is that we will not exclude the possibility that the maximum is achieved also somewhere in the interior. Indeed, that's never possible because you could just have a constant function, and then of course a constant function achieves its maximum in every single point. But as before in the elliptic situation, there are actually results about maximum principles, which are so-called strong maximum principles, which exclude the possibility of having an interior maximum unless your function is actually constant. But here we're just going to prove this result, theorem 4.3, which is called a weak maximum principle, namely that the maximum values are the same when I take it over the whole domain or when I take it over the parabolic boundary. So in the second step, we now want to assume that W is just as in the theorem. So I have Wt minus Wxx is just less than or equal to 0 in omega t. Then let me modify my W to get a W epsilon for epsilon greater than 0, which satisfies that W epsilon t minus W epsilon xx is less than 0, strictly less now. So how can I modify here? I can either add some function which depends only on the spatial variable and which has Laplacian positive. So I could, for example, add epsilon times x squared. I can just as well add a function which depends on time and has a negative time derivative. So I'm going to choose this, and I'm going to define my auxiliary function W epsilon to be W minus epsilon times t. Then taking this expression is simply Wt minus Wxx, and then I get a minus epsilon from here. So since this is less than or equal to 0, the whole thing is strictly less than 0. So by step 1, I can say something about the maxima. So I get that the maximum over the parabolic boundary of my domain of W epsilon is the same as the maximum over the whole thing of my W epsilon. Now I want to bound the maximum of W over the whole domain, and of course trivially whenever I take the maximum over the larger domain, I'm going to get something which is no less than the maximum over the parabolic boundary. So I'm really looking for an upper bound on the maximum of W. So the way I want to continue here is with a greater or equal to something to do with the maximum of W, and on the other hand I want to get something using the maximum over the parabolic boundary in there. Now, if I look at the definition of my auxiliary function, I immediately see that W epsilon is less than or equal to W, so I can bound the left-hand side just with the maximum over the parabolic boundary of the function W itself. On the other hand, here I have W epsilon, I subtract the term which is at most epsilon times capital T, so this here is greater or equal to the maximum over the whole thing of W minus epsilon times capital T. So we conclude that the maximum over everything of W is less than or equal to what I claim it is, namely maximum over the parabolic boundary, and in the first step still with an error term which comes of the form T times epsilon, where T here, this capital T, is just a finite number. So this holds for every single epsilon positive, and letting epsilon go to 0 gives the claim, as we trivially have, that the maximum over the parabolic boundary over the domain of W is always less than or equal to the maximum, and letting epsilon go to 0 gives me the non-trivial inequality. Hence I do have equality as I claimed in the theorem. So this completes the proof of the theorem. As said, that's the last theorem of the course, but we celebrate it with a small corollary, and this is corollary 4.4 about the linear application. And then in next step, we're also going to do a non-linear application. So first about the linear equations. Now in this course, we don't have the tools to establish existence of solutions of our heat equations, in particular not heat equations on general domains where methods such as separation of variables and so on just don't work. But we can talk about the other two aspects that you need in order to get well-posedness. And these are going to be okay for the corresponding linear equation. So let me consider the following initial and boundary value problem. So on the one hand, we look at the heat equation with some kind of right-hand side. So I have Wt minus Wxx is given by some function f, and I want to consider this in omega t. And then I want to consider initial values. So I prescribe w at x t equals 0 to be some w0. And then I'm prescribing w is equal to some function g1 on c1, respectively w is some function g2 on c2. So I have initial values, boundary values, and a parabolic PDE. So that's something where we hope we have well-posedness. Then what we can say is if the solution exists, and yes, the solution exists, but I'm not going to be able to prove this, so I'm not going to write it in the corollary. But if we assume that the solution exists, we also know that it is unique. And it depends continuously on the data. So the proof of this is extremely quick, or at least it's extremely quick for me, because I'm just going to tell you that this is your job and this is part of problem sheet number 4, where you're going to prove this. The proof is very similar to the elliptic situation that we've covered already in the last video. Instead, I do not want to finish this course leaving you with the impression that the maximum principle is only useful to analyze linear problems. Indeed, it's a very useful tool for a lot of nonlinear situations, and it's one of these results which is actually very simple enough to see in a second-year undergraduate course, but at the same time powerful enough that it's a major tool in the current research in many fields to do with analysis and also other areas of mathematics. And indeed, maximum principles can be used all over the place because a lot of things in mathematics are described using partial differential equations. And now a particular instance where this has played an important role was in the resolution of the one millennial problem that has actually been solved, and that's the resolution of the Poincaré conjecture. So this conjecture, which is really a statement in topology, this was proven using methods from differential geometry and from the analysis of partial differential equations. Namely, it was solved using the so-called Ricci flow by Perelman. And one of the important things when you have this Ricci flow, this is sort of a geometric version of a heat equation, is that you need to control how certain geometric quantities evolve in time. But because this Ricci flow has a sort of basic structure of a heat equation, there's actually maximum principles which are quite similar to what we have done that apply there and that allow you to control geometric quantities and compare them with some kind of solutions of explicit ODEs that you can solve. So of course I'm not even going to try to explain how any of this works, but I want to end this video by giving you some example of a nonlinear application, and in particular an example that shows you that you can use the maximum principle not just to look at one solution of a PDE in isolation, but also to compare different solutions of PDEs, even in a situation where it's not a linear PDE. Of course, if you have a linear PDE like this situation, and I take two solutions of the same equation, maybe with different data, the corresponding difference will still satisfy a PDE. That's just completely wrong if you have a nonlinear problem. However, the strength of the maximum principle is that you don't need that your function satisfies some particular equation. All you need is an inequality. And so in practice, what that's going to mean is that if we look at the nonlinear problem, all we need is the right type of monotone behavior of the nonlinearity. So the application that I want to consider is the following. So let's assume we have two solutions, W1 and W2, of a PDE. And the PDE I want to consider is Wt minus Wxx is equal to something nonlinear in W, say something like W to the 3. So the precise form is not important. What's going to be important is that on the right hand side, I have a function which is monotone increasing in W. So let's assume we have those two solutions, and let's assume that the data for these solutions is ordered. So I want to ask that I have W1 is strictly larger than W2 on the whole of the parabolic boundary. So both the initial values and the boundary values of the first solutions are larger than the one of the second solutions. Then what I'm going to claim is that W1 is larger than W2 on the whole of my domain, omega t. So how do I prove something like that? Well, first of all, the easiest way of approaching this problem is to argue by contradiction. So instead of trying to show it directly, we're trying to understand what would it mean for this condition to fail, and how could we apply the maximum principle to get a contradiction from that. Now the trick is going to be that we don't want to work on the whole domain at the same time, but we just want to go to the first place, the first time really, where things go wrong. So we have this domain over here that we've considered before, and I know at the start time in particular that W1 is strictly larger than W2. In particular, having a strict inequality means that my continuous functions W1 and W2, they will remain ordered at least for a little bit of a time. And then what I want to say is, if things go wrong eventually, there must be a first time where things go wrong, and I'm going to call this first time capital T star. And now instead of considering the whole omega t and applying my maximum principle on the whole thing, I'm just going to apply the maximum principle on omega t star. And now the trick in all of this is that the parabolic boundary of the smaller domain omega t star, so these are these three parts of the curves, this is of course contained in the parabolic boundary of the original domain, because this top line here, very importantly, is not part of the parabolic boundary. So how does this now work precisely? So I'm going to choose t star, so this is a number less than t, so that up to t star, before that everything is okay. So I want W1 is strictly bigger than W2 on the corresponding domain where t is less than t star and the corresponding points are in here. But then I want this to go wrong when I approach t star. Now, of course, I cannot jump from having a strict inequality like that to having an inequality in the other direction, a strict inequality. But rather what needs to happen is that I have at least one point at this time t star where things go wrong, where I have equality. So let me assume t star is so, and so that there exists some point x star, so that the W1 of x star t star is the same as W2 of x star t star. Now what does that tell me? So let me first note that as W1 is strictly larger than W2 on the set t less than t star, then just by continuity I can turn this in a weak inequality holding up to and including t star. And now, because I've chosen a nonlinearity which comes from a monotone function, a monotone increasing function, I conclude from this that w to the 3 is of course greater or equal w2 to the 3 on the same domain. So what does that tell me? I can conclude that if I take the difference w, which is w2 minus w1, then this will not solve a PDE because I have a nonlinear problem, but it will solve the right type of inequality to apply the maximum principle. So this w, this satisfies that wt minus wxx, so I first get the operator for w2, that gives me a w2 to the power of 3, and then I get minus the corresponding thing with w1, so that gives a w1 to the power of 3. I said this is greater or equal to this, so this is less than or equal to 0 in the whole domain up until the first time where things go wrong, so in omega t star. Now what does that tell me? So by the maximum principle, thus I conclude that the maximum of w over the whole of omega t star, this is equal to the maximum over the parabolic boundary, omega t of w, but because w2 is strictly less than w1, this is actually strictly less than 0. And that gives me a contradiction, because I assumed that w at the corresponding x star, t star, is actually equal to 0, which is of course not strictly less than 0, so I can't have this. So what does that mean? I've said if something goes wrong, there must be a first time t star where things go wrong, but at this first time where things go wrong, things don't actually go wrong, because I'm actually getting that w is still strictly less than 0 here, so things can never go wrong, and that means my statement must be true, and that means I've proven this little result at the end of this chapter. So this is a typical example how you can use the maximum principle to compare two solutions of a PDE, and indeed if you look carefully at what we've done here, we wouldn't even have needed that W1 and W2 solve this PDE. It would have been enough if one of them is so that the corresponding condition is satisfied with a greater or equal to 0, the other with a less than or equal to 0, and we would still preserve this ordering of two functions. So now you might ask yourself, well, how does that help me if I have no idea what the solution W1 does? How should I know what the other solution W2 does? But a particular example where you could actually apply this result is leading us back to the very beginning of the course, where we're studying ODEs. So of course you could also just take a function which doesn't depend at all on the spatial variable, then your wxx just goes and vanishes, and you're left with a function where you prescribe wt is equal w to the 3. So one way of applying this result is to compare a solution, say w1, with a corresponding solution of the ODE w dot is equal w to the 3 that you can solve explicitly, and that will give you already some initial information about how the corresponding solution of a parabolic equation has to behave. And with this example, we are now also at the end of this particular lecture, and therefore also at the end of this course. So I hope you had some fun seeing different aspects of PDEs and of ordinary differential equations. So you have seen there's already a lot that you can do, like proving existence of solutions of ODEs, analyzing in a qualitative way the behavior of systems of planar autonomous systems, solving PDEs using the method of characteristics and the transformation into normal coordinates, and now analyzing solutions of PDEs using the maximum principle. You've also seen that there's still a lot that you cannot do, in part because we don't have time in this course, and in another part because you don't have the required prerequisites from sort of infinite dimensional analysis to do quite a bit on the theoretical side, but I'm hoping that you're going to see more of that in the future. So I thank you very much for your attention for this course, and I wish you all the best. Goodbye, everyone.